So you're going to need this video for your homework assignment for Friday evening. This is a video that will go through your 4.5 notes. Then I'll do the one for your response question in the back of the notes. And then I'll actually do 2 examples from the 4.6.0 homework sheet. So if you feel like you're comfortable with doing the last 2 pieces on your own, you have the option of pausing and stopping the video. So I'm going to start off with the warm-up. If you want to press pause and try that warm-up on your own. So it's asking you to find the equation of the tangent line at x equal to 1, so you need a point. And the point would be f of 1, which is 1 squared, gives us 1. So the point we're going to use is 1, 1. The second piece is the slope. We find that by finding f prime of 1. F prime is 2x, therefore 2 times 1 gives us 2. So the equation of the tangent line that we know is the point slope form. And then what we're going to do is substitute in the point and the slope. So that tangent line would be shown here. Kind of like that. Not the best looking tangent line, but you get my point. So I'm using red purposely, and I use the blue function also purposely. If you look at the curves underneath here, you'll notice that it's actually all the same function, x squared. I am looking at x equal to 1 at all of them. And then the graphs actually look different, but they're not. So what I did was I essentially just kept zooming in, zooming in, and zooming in. And what happens is, because I zoomed in so much, the curve appears to look exactly like the tangent line. And that's what local linearization says. It says, essentially, if you zoom in enough, you should be able to see that the tangent line and the curve are the same. And this is because if f of x is differentiable, then f of x will look like the tangent line in the neighborhood of the point of tangency. And I actually have to say the point of tangency because let's look at the original graph. If I look at my tangent line and I start to extend my tangent line, you'll start to notice that the curve and the tangent line get further and further apart. But the closer I get to the point of tangency, which are the 4 that are down here, those end up looking just like the tangent line. So one thing I want to mention is, what if we look at y equals the absolute value of x at x equal to 0? Well, we know what that curve looks like, and we also know that no matter how much I zoom into the vertex here, the vertex always looks like a v, no matter what, no matter how much we zoom in. And that is purely because, let's see, y prime of 0 does not exist. And it doesn't exist because there's no local linearity. Okay? Now, let's see. So I'm going to write the equation of the tangent line. Just try to make this little, which would be y minus, let's see, y1 is equal to m times x minus x1. And then, given that, if I was to rewrite it in function notation, remember if you have a point x equal to a, then the y value is f of a. So I'm actually going to use that. So y1 is f of a, and the slope would actually be the derivative at a, and then x minus a. And then if I wanted to get y by itself, I could actually add f of a, the y value, to the right side. And it would look pretty much like this. It looks a little bit, not as nice as the equation I've given you the point slope for, but it means exactly the same thing. And that's what local linearization is. It takes the equation of the tangent line, and I'm going to use the one that's listed here, y value plus the slope times x minus a. And all it does is it takes the y value and replaces it with this new notation. Now, you're going to notice that as I do local linearization, I don't use this equation. I stick with the equation of the tangent line because I already know it. But then I'll turn it into this form. Now, this piece here, this whole entire thing just means y value. So, the example below says find the linearization. So, literally, when you see that word, I want you to think tangent line. What does that mean? So, it means just find the tangent line. Get green. Alright, so tangent line says I need y of 1, centered at 0. Y of 0 is equal to 1 plus 0, which is 1. Y prime to 0, chain rule, there's your power. Leave the inside alone, times the derivative of the inside. Y prime of 0 is equal to 1 over 2 root of 1 plus x, which gives us 1 over 2. So given all of that, I can find the equation of the tangent line, which would be y minus the y of the point is equal to 1/2 times x minus the x of the point, which was 0. So, moving the y, the 1 over, I get 1 plus 1/2 x. And then writing as linearization, I would say the center was 0, 1, the point where I took the equation of the tangent line, and the right side would be 1 plus 1/2 x. So it's exactly the same thing as a tangent line. The only difference is you have to write a different notation. But it's used exactly the same. So in terms of drawing the tangent line, not the best, but here it is. There's the tangent line. And the next piece, I'm going to use a calculator for this part. Oopsie, get that out of the way. So I'm actually setting up my calculator. I put the linearization in y1. I put the function in y2. I set up my table so that I can put in my own x values. So independent is at ask. So when you go to the table, it's going to be empty. And then I can put in my values. So I'm typing this right. Alright, so what I want you to notice is looking at the screen, I want you to look at the y1 versus y2 values. So in your notes here, you would copy down, linearization that I used was that y equals 1 plus 1/2 x. And then the function was y2, which was the root of 1 plus x. And I just want you to look at the difference of the values. What you'll notice is that they're really, really close. And the whole reason is because I'm looking at x values that are extremely close to the center. The center is where I got the tangent line, 0. Alright, so press pause and go ahead and copy down the table. So I think there's a piece missing down here. There it is. Alright, so the part that, oopsie, I didn't get to go over yet was this over and under approximation. So I'm going to show you what it means to be an over approximation versus under approximation. Let's just start off with understanding over approximation means that the tangent values are bigger than the actual, and the under approximation is that the tangent value is actually less than the actual. So then there's actually a way for this to always occur. And let's just start off with the over approximation. I'm going to graph a function that's both increasing and decreasing. And what I want you to notice is if I draw a tangent line, let me change my color here. So if I draw a tangent line here, do you notice that the tangent line is on top of the curve? And what I mean by that is pick an x value right here. This y value on the blue tangent line is higher than the blue point on the curve. What that means is the tangent's above. But you'll notice over here, if I do it again, now the tangent line's below. And the reason this is happening is because analytically and algebraically, if you find the second derivative at wherever you're trying to figure out if it's an over or under approximation, you're going to find that value. And if that value is, let's see, negative, then the tangent line will 100% be above the curve. So we have that happen as a result of the function being concave down at the point that they're asking. And then here, we're going to have concave up. And I'm going to just show you. I'm going to show you that where the curve is concave up along here. There's one, and there's one. Both of the curve points over here to the right, and I'll do this in red so you see it a little better. So this point on the curve is actually above the tangent line, so the tangent line is an under approximation. But over here, when it's concave down, the tangent line is above the curve. So that's the rule that you're going to end up using. Okay? So here's where I'm going to do my example. Let's just start with part A. So using what's given, figure out where you have your horizontal tangents. So those are my horizontal tangents. I can see that I'm going to find max and min, so I'm actually going to find where my h prime is also undefined. So starting off, h prime equal to 0, so x squared minus 2 equals 0. X squared equals 2, therefore x equals plus or minus the square root of 2. Undefined would be where x is equal to 0. So I'm going to do my sign chart over here, h prime. I'm allowed to use any value except for 0. It's undefined because the function's not defined there, so let's cross out those values, and then plus or minus root 2. Oopsie. Sorry. Alright. 0 and 0. And the function I'm looking at here, if I put in negative 1 million, I'm putting this into my derivative. Negative 1 million, top would be positive, bottom would be negative. Negative 1, top would be negative, bottom would be positive, negative also, so make it positive. Positive 1 would make the top negative but the bottom positive, and then the very last, 1 million, would make the function positive. And so the question asked me for where I have local maximums, minimums, or neither at each of the values where the function has a horizontal tangent. So it looks like the function goes down, flat, up, down, flat, up. So we have two minimums. So at x equals plus or minus root 2, we have minimums. And notice here it says justify your answer. So because f prime of plus or minus root 2 is 0 and f prime changes positive to negative. Alright. Part B, on what intervals is the graph of h concave up? So h prime of x, I want to find the second derivative, so I'll do a quotient rule, low, d of high minus high, d of low, all over low squared. I get 2x squared minus x squared plus 2. Make sure you distribute your negative all over x squared. Let's clean that up. We get x squared plus 2 all over x squared. H double prime of x equals 0 when x squared plus 2 equals 0. X squared cannot equal negative 2, therefore I have no values, but h double prime of x equals undefined when x squared equals 0, therefore x is equal to 0. Let's see, that says 2. So I'm going to do a h double prime sign chart. And all I'll have in the sign chart is 0, which is undefined, cross out because it's not in the domain. And you'll notice, given the second derivative here, the values are always positive. So the question was, when is it concave up? It is concave up from negative infinity to 0, union with 0 to infinity. Part C says to write the equation of the tangent line at x equal to 4. Now, I believe they gave us h of 4. They said the value was negative 3, so we need that. And actually, let me change my color over because I might bleed into the other work that was there. Alright. H prime of 4 would be, I believe that was x squared minus 2 over x. So 4 squared is 16 minus 2 is 14 over 4, which is 7 over 2. The equation of the tangent line then would be y minus negative 3 is equal to 7 over 2 times x minus 4. And then part D asks you if the tangent line is going to be above or below the graph. So that's literally the same thing as an over or under approximation. So for part D, at x equal to 4, the second derivative is positive. What that means is that at that point, the graph is concave up. So no matter how the graph looks, if I know the graph is concave up, then we can just draw a quick tangent line to test. It's not the tangent line, but the rule works that anytime the graph is concave up, then we know that the tangent line will follow this behavior. So now as a result, we can see that the tangent line lies below the graph. Alright, so the next page actually has a scoring guideline. So if you did it on your own, you can actually check if you got a 9 out of 9. Multiple choice example for you. Approximate the value, and contrary to what it looks like, this is actually a non-calculator problem, and I'll show you in a second why. Obtain from the tangent to the graph, and this is our center. This is where I'm actually finding the equation of the tangent line. Oh, shoot. So, y of 0 is equal to the square root of 4 plus the sine of 0. So, the sine of 0 is 0, so the root of 4 is 2. And then y primed of 0, first I got to find the derivative. That's a chain rule with a power of 1/2. Times the derivative of the inside, which is cosine of x. I'm going to find this at 0. So let's clean this up a little bit so I know what I'm looking at. So I do this because I'm evaluating, and I don't like evaluating with negative exponents because it is confusing. So next piece, the cosine of 0 is 1 over, and we know this is the square root of 4, so we actually get 1/4. Alright, obtain from the graph. So, write the equation of the tangent line, which is y minus 2 is equal to the slope times x minus 0. We're approximating at the value where x is 0.12. So you'll notice I didn't even bother trying to write this in linearization form. So there's, oh my lord, I have no idea why that keeps happening. Alright. And then I'm going to add 2 to the other side. Holy crap. 2 plus 1/4. 0.12 is the same as 12 over 100. So that would be 1, that would be 3. So y is equal to 2 plus 3/100ths is the same thing as 0.03. Therefore, it's 2.03, which is letter B. Alright, and then I said I would do a little bit of review for your homework. So if you want to take out your homework packet, 4.6.0 towards the back, you want to find that worksheet. I'll do number 1 from this page, and then number 1 from the 3rd page, I believe. So this is a reminder of implicit differentiation. To find the derivative with respect to x, that would be 2x plus, be careful here, since I'm doing y's, I need the derivative of y with respect to x, and then the derivative of a constant is 0. dy dx is equal to negative 2x divided by 2y, and we get negative x over y. This one's slightly different because of this piece. It says that you want to take the derivative with respect to t. So now, since all the variables are not t, I'm going to have more differentials. So x squared, the derivative would be 2x, but multiplied by the derivative of x with respect to t, plus 2y times the derivative of y with respect to t equals 0, and therefore 2y dy dt is equal to negative 2x dx dt. And then this is a differential, so I don't need you to try to get common denominators with that. So dy dt is equal to negative x dx dt over y, which is the same as negative x over y, and then multiplied by dx dt. That's actually the same thing. And then, one last example. We'll do number 3 from this page. Number 3 says, this whole piece, letter A, is actually part of the problem. So we're going to find dy dt. Let's start with the fact that this is a dt problem. And because it's a dt problem, that means that we will do the derivative with respect to t. This is a product rule, so leave the first one, derivative of y with respect to t, plus leave the second one times the derivative of x with respect to t equals 0, because it's a constant. And then it says, find dy dt when x is equal to 8, so 8 times dy dt, plus y times dx dt, which is 10. And the problem is I still have this y sitting in here, but remember functions. If I know my x, I should be able to find my y. So when x is equal to 8, then 8y is equal to 4, therefore y is equal to a half. So I get 8 dy dt plus 1/2 times 10 equals 0. dy dt is equal to negative 5 over 8. That's what you're doing for the start, or kind of the intro to related rates. There is everything for you.